feel like blue is always good.
Hello and welcome to Colloquium. It is our great pleasure to have a talk today by Professor Konstantina Trivisa from the University of Maryland, both the Department of Mathematics and the Institute for Physical Science and Technology, where she is currently the director. Konstantina is a force of nature, which I learned in every interaction I ever had with her, and which I've heard from everyone who ever interacted with her. She's passionate about what she does, and it's really infectious. And so I always enjoy learning from her, both about mathematics and Maryland, and pretty much everything. So without further ado, welcome.
Thank you. Thank you, Alex, and thank you for the invitation, and thank you all for being here today. I thought that Cornell would be the ideal place to present this work because of its connection with Richard Feynman, who has been credited with pioneering quantum computation. So, as Alex mentioned, I have two affiliations. I'm an applied mathematician, but I'm also director of the Institute for Physical Science and Technology. And I should mention here that the most distinguished member of our faculty, we lost in the last few days the most distinguished member of our faculty of the Institute that had very strong ties with Cornell, Michael Fisher, one of the giants in science, statistical physics. And what I learned the last few days is that when he was at Cornell, he had a joint position at the Department of Chemistry and at the Department of Mathematics. I was not aware that he was a faculty of mathematics, but I remember him speaking fondly about the years that he spent at Cornell. So today, I'm going to present some results on the construction of an efficient quantum algorithm for dissipative nonlinear partial differential equations that arise in fluid dynamics, plasma physics, epidemiology, in areas of science where the dimensionality of the system is high enough to necessitate the use of quantum computing. So, as director of IPST, I'm interested in okay, I hope I will find it again. I'm interested in enhancing the collaboration between, I don't know if I will find it, between industrial and government partners. And this result that I will present today is a product of such a cross-sector collaboration. So I'm not sure what I have to do in order to bring this up. I'm sorry about this.
Let's try a software engineering approach. Turning code.
Plug it in, plug it back in.
Yeah.
And I promise I will change the slide faster. So, in any case, let me say.
So sometimes if you close the lid and plug it in, it finds the source again.
So let me.
Does it look like your background?
No.
No?
Seriously though, if you close the lid, sometimes it's
Close the lid.
yeah, unplug it and plug it back in. Oh,
Let's be dangerous.
Exactly. Thank you.
Chris.
All right.
Technical support.
So as I
This is your
mentioned,
number.
this work is a product of such a cross-sector collaboration, and let me present the research team that it is involved. So this is a work that involves three academic institutions: University of Maryland, MIT, and Norwegian University of Science and Technology, one industrial partner, Raytheon BBM Technologies, and several people, starting with Adri Childs, which is the director of Quantum Information and Computer Science, QUICS, at the University of Maryland, which has been created thanks to the support of the National Institute of Standards and Technology. Nuno Loureiro, who is in the Institute of Plasma Physics at MIT, Thierry Crovi, he is a senior scientist at the Raytheon BBN Technology. And of course, we have two students. Chip and Yu was a student, is a student in the AMS program that I admitted. And unlike some of the people that I had lunch today, he accepted my offer. So, Chip and Yu, admitted by me, has produced this wonderful result as the lead author of this paper. So this work provides an exponential speed up for a class of nonlinear systems of differential equations. And it received a lot of attention because of that. There was coverage at the Quantum magazine. And of course, there is a paper that has just appeared in the proceedings of the National Academy of Science. So let me start with the outline of my talk. I'm going to start with a very brief introduction on quantum computation and this idea of storing and processing information. Next, I'm going to present the quantum simulation problem. And I'm going to start preparing the stage in order to present the main result, which is the construction of an efficient quantum algorithm. For nonlinear differential equations expressed here, you're going to see as quantum quadratic ODE problem. And you're going to tell me, oh, you started talking to us about nonlinear PDEs and now you are referring to the quadratic ODE problem. Well, it turns out that under certain discretization, appropriate discretization, many interesting nonlinear PDEs can be casted in this particular form. And you're going to see that the Navier-Stokes equations is part of it. Several models in epidemiology can be casted in this framework. So when I present the theorem and the main result, it will be in the context of this quantum quadratic ODE problem, but at the end, we are going to see a class of systems which can be casted in this form and for which the result applies. So here, we are in the mathematics department. Of course, the director of the center is a computer scientist, but I want to emphasize the crucial role of mathematics in this world. So the result is obtained by using an applied math technique that it is rather old-fashioned and it had never saw a lot of action in the past. It is the so-called Klarman linearization. So this is a way of mapping a nonlinear system of partial differential equations into an infinite dimensional system of linear equations. So you realize what is happening. Of course, when you have a system of linear equations, we know, the applied mathematicians, we know that we can do a lot of things. First of all, even if it is infinite, we can truncate it to bring it to the resonant size. We can use all these discretization methods, forward Euler. We can do error analysis, and we can obtain a lot of insight. So, but the thing that gave us the idea to use this linearization technique, for which we provide a rigorous convergence theory, etc., was the fact that there exists a well-known quantum linear system algorithm, which we realized that could be of use. So this is the tools that we are going to use throughout my talk. I should mention that at the center of all this work, there is a parameter R. This parameter, intuitively speaking, resembles the Reynolds number. Let's say in the context of homogeneous ODEs, will have been nothing else than the Reynolds number. In this context, we consider this a parameter which quantifies the strength of the nonlinearity and the driving force relative to the dissipation. So you realize when you have a nonlinear systems, there are various types of nonlinearity. And it will be naive to believe that you can obtain efficient quantum algorithms for every nonlinear PDE. So our result here is obtained with reference to the number R, which is a measure of the strength of the nonlinearity and force relative to the dissipation. So the second part of my talk will refer to hardness of state distinguishability. And this is one of the most known phenomena of quantum mechanics, this property of superposition. You know, if you have a classical bit can be either in state 0 or 1. If you have a quantum bit, a qubit as I will be calling, the electron, let's say, can be either in state 1, state 0, or in both states at the same time. In fact, it can be in any linear combination of these states. So there is a very big need to understand what needs to be done in order to be able to distinguish the states. And then, as part of this discussion, we are going to obtain a lower bound above which the problem is intractable. So we are going to see that when the nonlinearity is extremely strong, then there is no way to create an efficient quantum algorithm. And what do I mean when I say efficient quantum algorithm? So this notion of efficient or inefficient quantum algorithm has been made precise by the mathematical theory of by the complexity theory, mathematically rigorously by complexity theory. So roughly speaking, an algorithm is efficient when you can perform the task in time polynomial to the size of the problem. And you can have complexity in terms of the time or in terms of space. So the question is, how much time do you need to use in order to perform the task, or how much memory? So this is the issue that we are going to address as I move along. So at the end, as I mentioned, you are going to see that there are indeed some applications in physics. The equation that we will focus on will be Navier-Stokes equation and related models, and some big systems that arise in the epidemiology. Okay, so let me start going. So the outline of my talk is the following. Oh, we said that. So let's get started. So this is a work about quantum algorithms, about what you can do using quantum computing. So let's see how the story begins when you have information that needs to be stored in states. So in quantum state, in the states of the mechanical system, then this process of storing information uses a lot of quantum mechanical properties. And the device that can perform these operations and properties can do certain things that are mentioned here, can potentially speed up exponentially the time of performing the task, or super polynomially. So, and there are examples in, I have mentioned some here, for which already we know that there is exponential speed up if you use quantum mechanical properties. Such an example is the famous factoring problem. And I mention this because we are in the Department of Mathematics. So the factoring problem was resolved by Peter Shor in 1994. And the factoring problem can be stated very simply. It says, given an integer num, n, find its prime factors. So when Peter Shor showed that there is an exponential speed up on this problem using quantum mechanical properties, the field of quantum information and quantum computing took off immediately. And the reason was that there is some implications about this result with cryptography. People certainly got worried that this will have potentially there is a security problem, and people will be able to crack codes and develop a lot of bad acts. So I say here, and I believe that quantum computers. This is another important point, is that recently there is a lot of effort to see how quantum computers can help for problems in numerical analysis. And this will be relevant to the topic of this talk. So the big task about working on problems of numerical analysis is this question whether you can represent a vector in the Hilbert space of a quantum mechanical system. And this is where I want to go. So let's focus on this idea of representing vectors directly in the Hilbert space of a quantum mechanical system. So if you have a vector x, then it is a complex, this is an n-dimensional vector in the complex plane. And the main idea of this class of algorithms is to represent these n-dimensional vectors by quantum states. This is the notation by which we denote quantum states, introduced by Dirac. So the idea is to represent this vector by quantum state of log 2n qubits. This is the first step. Why do you want to do that? Because that will provide a very compact representation of the solution. So, and if you are able to prepare such a state, and during my talk, I'm going to give a hint about what do we mean by this idea of preparing a state. And the idea of preparing a state, as we're going to see, relies on performance of quantum measurements. So when a mathematician listens to the words quantum measurement, the first thing that you should have in mind is sampling. Of course, when you're performing sampling, there is a probability distribution associated with the effort. So in order to prepare the state, you have to do some analysis that will allow you to know, let's say, which states are let's call them good, and which task can give you a good probability of success. So, but this is what I mean here. If we were able to prepare such a state using polynomial in the log of the dimension operation, then we will have really a very compact representation of the solution. So this process, as I mentioned here, produces a quantum encoding of the solution. This quantum encoding is much less informative than what you get when you run MATLAB. When you run MATLAB, you get the solution explicitly. You say x is equal to this vector. This is not what you obtain in this particular setting. But you can get it much faster, and it can be potentially useful. Okay? So, and as I mentioned earlier, one of the other important needs for advanced quantum computing is because it will help us simulate physics. And this is what brings us to Feynman. So it was Feynman in the 1980s when he observed that performing quantum computations, simulating quantum mechanics, can be a very, very hard problem for classical computers. So in his mind, it was like a brute force attempt to represent a quantum state. So he realized that something else is needed. And then he proposed this, the so-called quantum simulation problem. So the quantum simulation problem, which I state here, says something that can be stated very simply, given the description of the quantum mechanical system. So when I say given a description of the quantum mechanical system, means given a Hamiltonian that describes the dynamics of the system. So when we give a Hamiltonian, which is a mathematical object, in reality what we give is the physical description of the system. Okay, because this Hamiltonian really gives us information about the dynamics. So given the physical description of the system, given an evolution time t and an initial state c of 0, the problem asks you to produce the final state, and of course you will be happy to do it exact, but even if you cannot do it exact, at least you should be able to do it with certain tolerance. So what is the story? The story is that a classical computer can not even represent the solution efficiently. Because if you have a very large system, a very large vector, even writing the vector down requires a lot of memory. So, and what here I'm emphasizing is the following, that a quantum computer cannot produce a complete description as as I mentioned earlier, but by performing measurements, it can answer questions that apparently a classical computer cannot. And I believe when I write here that the quantum simulation is one of the most compelling potential applications of quantum computers. And the reason is that we really feel that we can have a very big speed up. And this speed up will be critical for areas like quantum chemistry, condensed matter physics, nuclear particle physics, several problems in biology, where the dimensionality of the problem is large enough to necessitate the use of these quantum computers. So, but there is another sense in which this idea of Hamiltonian simulations can be very useful. Okay, and this is the following, the one that I'm going to explain right now, is the fact that we can use it as a tool in order to implement quantum algorithms. So there are several quantum algorithms that can be phrased in terms of a Hamiltonian, where this idea of running the algorithm is equivalent to simulating the dynamics of some Hamiltonian. And there are various examples that one can mention. There are the so-called quantum adiabatic optimization algorithms. These algorithms, they use usually the adiabatic theorem of quantum mechanics, which basically enables us to find the minimum of a function by interpolating between two Hamiltonians. Another class of quantum algorithms that have been very important are ones that rely on quantum walks. So quantum walks are the quantum analog of classical walks, and they are very important in the creation of randomized algorithms. There is a class of algorithms that rely on evaluating Boolean formulas, for which I would say nothing. And what the topic of my talk will be basically on algorithms that allow us to solve linear and nonlinear differential equations. Okay, so this is where the story goes. So, well, I will say here that the workhorse that makes the transition from the Hamiltonian simulations to the abstract quantum linear algebra problems is the so-called quantum linear system algorithm. So this algorithm tells us some simple things. Given an n by n system of linear equations, and let me write it ax equal b, the question is how can we find the solution x? If A is invertible, we know that this will look something A inverse B. And classical or quantum algorithms need time at least linear to the dimension, just to write down the vector x, and even more, even if you can use Gaussian elimination, for instance, and you will need at least this amount of memory in order to write down the vector. And the question that one can ask is, what about if we change the model? What about if we decide that, we are not going to try to solve this problem in the classical sense, but we are going to follow the principles and the ideas of Hamiltonian simulations. And what we are going to ask, instead of solving the problem, is to prepare a state, a quantum state, that it is proportional, normalized, let's say proportional, to A inverse quantum state B. So, of course, in order to do that, you will need some additional hypotheses. You will need to impose certain conditions on the matrix A, for instance. In this setting, A would be required to be a sparse matrix. So you will need, let's say, a certain number of zeros appearing in this matrix. And given a black box, you can think of it of a matrix, something that will allow you to specify the non-zero entries in a given row or column. And if we are able to prepare this state B, then the goal of this process is to prepare the state X, which is proportional to A inverse quantum state B. So this is where this story goes. So, oh, very nice. So let's see where we are going next. So let's see what we can say about this particular problem. This problem, in the case of linear systems, it was solved by the initial result were by Carlo, Hessing, Lloyd in 2009. And the answer was affirmative. They were able to provide such a state. And they had the ability to do this in time polynomial in the log of the dimension, and polynomial in the inverse of the error, and polynomial in the condition number. Okay, here is the condition number. The condition number is the number basically that determines how sensitive is a system in connection with the initial data, for instance. Very often it gives information about how singular is the matter. So this algorithm on the quantum linear system algorithm relies on these ideas that I mentioned earlier of Hamiltonian simulation and on this notion of quantum phases to estimation. So this process is a way to estimate the eigenvalues of A and the replacement of these eigenvalues with their inverse. So this is the way that this algorithm works, that you have to find a way to estimate the eigenvalues of A and replace these eigenvalues with their inverse. This is the idea of obtaining the inverse of the method. I should say that subsequent improvements have been obtained in which this original complexity rate has been improved to linear in the condition number and polynomial in the log of the inverse of the error. So now the whole idea is the following. Maybe we can use these ideas in order to say things for more abstract linear algebra problems and also for differential equations. So this is where the story goes, and the idea is the following. And I'm going to start first with a linear theory. Given a linear ODE with initial condition, here this is the ODE dx dt equal a matrix A epsilon x plus b with initial data x of 0. The goal is to determine x of t at some time t. So, as I say here, quantum simulation is a special case. It's a special case where this matrix A is either Hermitian and b is equal to 0. In reality, one can handle more complicated linear ODEs. And as I mentioned here, the main idea of this class of algorithms for solving linear differential equations is to approximate the dynamics by a system of linear equations. And this typically happens by introducing appropriate discretization, let's say the finite difference method, and to bound the approximation error, the condition number of the system, and the success probability for the procedure in terms of the properties of the ODE. And I will say more about this in some of the next few slides. So, as I say here, this approach came with some caveat. For instance, you have to follow the limitations that we had when we are discussing the quantum linear solver algorithm, in the sense that we don't provide an explicit description of the solution, but it is like a quantum encoding. Another important point that it will be very relevant very soon is that the norm of the solution cannot decay exponentially, because then the algorithm breaks down. This is something that it is not allowed even in the case of linear differential equation. And we're going to see that we are going to have an analogous property in the context of the class of nonlinear PDEs that we are solving. Okay, there are some improvements of this work. So we all know why nonlinearities are crucial, so this probably slide is unnecessary. There are many applications in plasma physics, in finance even. Actually nowadays there is a lot of effort from the Wall Street for people to get involved in quantum computing. And I should say that everybody is trying to do what I mentioned here to provide killer applications of quantum computing. And this is a very big effort that appeared within NASA, within DOE. There was this famous challenge, the Airbus Quantum Challenge. Very recently, Chris Monroe, who used to be a faculty at the University of Maryland, and now he's at Duke, he's the director of the National Quantum Initiative. And he gave a very well advertised, at least in the DC area, address to the Congress, where he claimed that what actually killer applications, basically this idea is boiled down to code breaking. And he explained various applications of science where these ideas of quantum computing has already produced some results, and these are in the context of optimization. So let's see what about nonlinear differential equations? Can we, this is the question, can we somehow provide such an algorithm that can handle nonlinearities? And the first attempt to achieve that was made by Layton and Osborne in 2008. In this particular case, the algorithm that they created for n-dimensional nonlinear ODEs for time t, so they were able to provide an algorithm with complexity that it is polynomial in terms of the log of the dimension, which is very nice, but it turns out that it is exponential in time. So what does this mean? That means that you can only hope to run this algorithm for a very, very short time interval. So what was the main idea of the approach that they used? The main idea was to use multiple copies of the solution in order to represent polynomial nonlinearity. So let's say that you have a quadratic nonlinearity, you will need to use, let's say, 2 copies of the solution. A quadratic, 4 copies of the solution. So what is the problem? The problem that they faced, and the reason that this didn't quite work, was that these copies typically are used as we evolve, and there is a famous theorem, the not cloning theorem, that says that we need to maintain all copies throughout the algorithm. So you can imagine that you have multiple copies that you have to keep evolving, and this leads to an exponential overhead. And I will state here what is the non-cloning principle, because it has implications. So the non-cloning principle is a fundamental property of quantum mechanics, which states that given an unknown quantum state, there is no reliable way to produce extra copies of the state. So this means 2 things. This means that the information encoded in quantum state is essentially unique. This is one way to see it. But now this has implications. So this is sometimes annoying when you want to protect quantum information from outside influence, but it can also be very useful in the context where you want to communicate securely with someone else. So there are 2 coins regarding this principle. There are some positive elements and some negative elements. So let's see something else. So we know that nonlinear dynamics can be computationally powerful. The question is, and it seems to be very hard to be simulated, very hard to obtain results. So what Chimpen, you and I thought is the following. Okay, we cannot do it in general. It seems that it is very difficult. But can you do something interesting, at least for physically relevant classes of nonlinear differential equations? And we identify such a class that, that has is connected with some very good physical applications. So here is what I'm saying, and we are going to see, as I mentioned earlier, I'm going to start discussing now the quantum quadratic ODE problem, and later on we're going to see its connection with certain very well-known partial differential equations. So let's consider the ODE. So we have du dt is given by this quadratic form. So here we have a linear operator acting on two copies of the vector u. We have a square matrix F1 acting on u, and we have an inhomogeneous term that depends on time. And you can see here how you can understand this. When you see this symbol, you have to think u tensor u. It is the two copies of the vector which is given here. So we have F2 and F1 are time independent. Assume that you are given an oracle to prepare a quantum state proportional to the initial state. And we need to have sparse matrices F0 of P, F1, and F2. We also assume that the matrix F1 is diagonalizable with eigenvalues lambda j which satisfy this relation. So the real part of these eigenvalues is non-positive. And this is exactly where, this is the characterization of dissipation. Okay. So when we were looking, we started discussing this issue with Chip and Liu, we were thinking about dissipation in terms of viscous stress tensor in the context of Navier-Stokes equation, viscous-Berger's equation, and so forth. But we realized that we can put it in the framework of an ODE, and in that case, really the dissipation can be characterized by a condition of the eigenvalue. So now what we decided to do is we decided to parameterize the problem in having in mind that we will not be able to do it for general nonlinear systems. We decided to parameterize the problem instead of the parameter R. And the parameter R has exactly this form. So what does this parameter R do? As I mentioned, is qualitatively similar to the Reynolds number. This parameter R defines the strength of the nonlinearity as expressed by the norm of the F2 matrix and the driving force relative to the dissipation. So whatever I'm going to discuss moving forward, it will be in connection with this number. So, and let's see where, let me present the first main result, which is an algorithmic result about our ability to solve this problem. So it says that if the parameter capital R is less than 1, so what does this mean? That this means that the problem is not too strongly nonlinear and not too strongly driven relative to the viscosity, then there is an efficient quantum algorithm for this problem. And specifically, as you see here, is complexity, let's see, scales linearly with respect to the sparsity, linearly with respect to this parameter Q. The parameter Q tells us how the solution behaves. It relates the value of the solution at time t with the values of the solution at the initial time. So this is an important quantity, and it is related to the statement that I mentioned earlier, that even for linear algorithms, you cannot expect to have an efficient algorithm if you have exponential decay, because the problem is really hard, they cannot be solved. So, but let's look something else about this quantity. So what we observe here is that really the complexity scales in nearly quadratic in time and not exponential in time. So we really have an exponential improvement regarding to the time, and this is very, very important. By epsilon here, we denote the error in the approximation of this normalized quantity. So what are the ingredients? I mentioned the ingredients earlier. It is the so-called Kahneman linearization. We're going to see in the next slide. We're going to consider forward Euler discretization, and I know from my lunch this afternoon that a lot of you guys know about forward Euler discretization. Then we're going to continue with the state preparation, and we're going to say a few words only about the condition number and the state probability analysis. So as I mentioned, to analyze the complexity of this approach, we provide an upper bound of the condition number of the linear system, and we need a lower bound of the success probability. So let's go to just introduce you to the Kahneman linearization. I'm sure that a lot of people have heard about this. So let's consider the scalar case. Let's consider a simple ODE here, linear ODE, quadratic ODE, du dt is equal to constant A, u squared, plus bu plus c. So what the Kahneman linearization method does is the following. You start with the first equation, which is exactly this relation, the ODE that we got with Kahneman. Then you say, okay, I know the dynamics of u. Let me calculate the dynamics of u squared. Calculating the dynamics of u squared means that you have to apply chain rule. You come here, du dt is given by the previous step, you place it, and you obtain this nice expression that provides the dynamics of u squared in terms of these three terms. You continue this process several times, the kth equation, the nth equation, and you realize that when you estimate the dynamics of u to the power k, then what you need is an expression that consists again of these three terms. It's a simple calculation, but you can see. So I will say it again because it is very interesting that this kind of process maps a system that it is a system of nonlinear ODEs, and then we're going to see a nonlinear PDEs, to an infinite dimensional system of linear ODEs. And now what we need to do is to truncate the system and to find what is the suitable number n for which we can get a very good approximation. So this is the form of the Kahneman linearization in the case where u is a vector. So now each time that you see this symbol means j copies of the solution. And in analogy to the previous slide where you saw that each member here of this vector, was written in terms of three terms, here in the general form we realize that we obtain a triangular matrix of that sort. And as I mentioned earlier, okay, if you reduce something to an infinite dimensional system, you are not still in a good shape. But we are applied mathematicians. We know how to truncate a system. And we know that if we do appropriate error analysis, and I'm only going to solve this slide, when you do error analysis, and this work provides the converters of the Kahneman linearization, even the quantum framework, but this is not scary for us, that we are applied mathematicians and we know that all we have to do is to introduce a quantity that describes the error. So we have the j copies of the solution, and this is minus the numerical solution. And we know that all we have to do is to see how this evolves in time. And by doing this, we obtain an estimate of this form that basically allows us to estimate this n. to tell you exactly, given the problem, what is the dimension that you should consider, so that in fact, to have a good approximation of the solution within a certain delta, let's say. And of course, in this process, what we will need to do, you will have to create a quantum ODE solver. So you will have to apply, let's say, a forward Euler method. When you have a forward Euler method, essentially you replace the time derivative by a quotient, yk plus 1 minus yk divided by a step. And this is what we are doing here in more fancy writing. This is what it says. And by doing this and by applying the radiation method, we are able to reduce the infinite dimensional system of linear equations to a finite system. So what else do we need to do? Okay, let me say a few words about the next issue. This slide shows a limitation of the quantum computing to distinguish states. A limitation to solving the quadratic ODE problem. So what is this limitation? Where when R is less than 1, when the nonlinearity is there, but it is not very, very strong, we were able to find an efficient quantum algorithm. What this theorem tells you is that when the nonlinearity is stronger than R, let's say the R here is greater than the square root of 2, then there is an instance of the quantum quadratic ODE problem such that any quantum algorithm for producing a quantum state of this nature with bounded area must have a worst-case time complexity exponential in time. And this result relies on two components. The so-called, the two ingredients are the hardness of distinguishing non-orthogonal quantum states and a quadratic ODE example that will solve that rapidly distinguish non-orthogonal states. So this is a dichotomy. In one case, we have hard time distinguishing. In the other case, something happens unbelievably fast. So here is the statement regarding the hardness of states distinguishability. It says basically that, let me say a little bit, let's consider that we have two states, and you see the state in the slides, the state psi, quantum state psi, and quantum state phi, that somehow form a very small angle between. They are very close to each other in the Hilbert space, so they have somehow a close angle. So this is expressed by this expression. So suppose that we are either given a black box that prepares the state C, or a black box that prepares the state phi. Then what the theorem says is that any bounded error protocol for determining whether the state C or the state phi must take time that it is inverse to the error of the problem. So if we use the box k times, in this sort of approach, we saw that produces state with a very big overlap here. And there is a very, very famous theorem, the Hellstrom bound, that says that in this particular setting, you need a lot of time in order to distinguish the states with bounded error. In the sense, you need k that is of the order 1 over epsilon. So let me give you a little bit more about this in the context of this example. We consider the ODE du dt is equal minus u plus ru squared. This is an ODE for which we can solve it explicitly. We know how to solve this ODE. And let this OD operator act on both basis states of a qubit. So the uniform superposition, what we can show is that if we consider the uniform superposition of this form, then does not involve up to normalization. But if we rotate this a little bit, so instead of having here 1 over square root of 2, I rotate a little bit the angle. So I have pi over 4 plus theta. Then there is an exponential change. And this is going to be given with this simple illustration here. So what does this say? This basically says that the quantum computer cannot manage this type of situation, this exponential change. And this is not the proof. The proof relies on lemmas and lemmas and lemmas. But intuitively, this is the intuition behind how this theorem works. Actually, this theorem works. And now that I have said some things about the theory, let's see about some examples. So what type of systems can be handled with this type of problems? For instance, high-dimensional ODEs with nonlinear coupling of this form that appear in math biology, in population dynamics. This particular ODE can be casted in the quadratic ODE problem. There is a lot of examples on epidemiology, like the SAR model, or we have a COVID-19 model. So let me give you this particular model. So this model is a system, a nonlinear system that corresponds to a pandemic, okay? So you have a certain pandemic and you have a population. The population of P individuals in a city is divided by susceptible people, people that are exposed, people that are infected, and people that have recovered. So this is denoted here as PS, PE, PI, PR. We denote by R a flux of individuals refreshing the population. And I'm considering these parameters are transmission rate and R vax, which is vaccination rate. And we also consider T-inf and T-lag. The T-inf is the infectious times that an infection person can infect others, and the latent time is the time until an exposed person becomes infectious. So what happens is that even this signal model, realistic parameters from the study related to COVID-19, showed that we can obtain an R which is less than 1. So the theory that we have described can potentially be used in models of that nature because, biologically speaking, it has the right property that help us obtain it is the type of nonlinearity that we can have. Of course, you are not going to use quantum computers if we were able to for a simple modeling of this form, but this model can potentially be generalized to model early spread over a large number of cities, larger type of populations, and in that case, it could be potentially useful. And of course, a classical example, and I will finish with this, is that for which can be casted in the form that I described are the so-called Navier-Stokes equations. Here we have used the flow velocity, and of course this equation describes various models in fluid dynamics, plasma physics, etc. So I wanted to say the following. Even though the original theorem has been proved only in the case when R is less than 1, that means that can handle nonlinearities that are strong but not that strong. In reality, some computational experiments show, in connection with a viscous-Berger's equation, that in this case, look, we have this PD. And as I mentioned to you earlier, you can write this PD in this system of difference equations. So here we use discretization. What is the discretization? We use central difference scheme. So it can be casted in the formula that we saw earlier. What can you do about this quantity? We're going to use forward Euler, and we're going to be able to integrate. Okay, so when we do that, what we see is that we can obtain, but this is an optics, it is not a proof. We can see that we have a good convergence even for Reynolds numbers that are large, extremely large, is equal to 20. So this gives us some hope that maybe we can have some potential by studying and understanding the dissipation mechanism better to say something that it will be even more reliable for a variety of regional of scales for the parameter R. So here you can see some description of the error. And let me give you a small summary, and we can see what we have shown so far. So we have shown how to efficiently produce a quantum equality of the solution of the system of dissipative nonlinear ODEs, provided that the nonlinearity and forcing are sufficiently weak relative to the dissipation, and the solution does not decay exponentially. This is something that we should always have there. And linear ODE are BQP complete, so the problem is classically hard. Exponential decay is a very big obstacle due to the hardness of the post-selection. And so basically this means that the problem cannot be tracked with quantum computing. It's PP hard. Dissipative non-driven ODE necessarily decay exponentially, so no algorithm for long-time evolution can be given. You can have an algorithm that will be used for a very short time. And of course we have shown that there can be no efficient algorithm for general nonlinear ODE for R greater than 2. And another interesting, I only here mentioned that numerical evidence suggests that we have to do more work in order to understand the concept of dissipation, because the fact that numerically we can see that we can obtain good convergence of the cardinal linearization method, even for R that it is 20, indicates that there is something that we need to understand more. And of course the significance of the result is that this is the first algorithm on nonlinear PDEs that we proved, we constructed, and it is efficient. We were able to establish a lower bound, showing actually, providing actually a very tight classification of the quantum complexity of simulating the problems. And now, what I'm saying here is something that all of us we are going to try to do. We are going to try to understand better the feature that we see in the context of the Berger's equation, so that we extend the algorithm in such a way that it's able to potentially characterize complex nonlinear phenomena in fluid and plasma. So what I want to say here, some immediate open questions that we are working to address, we have a characterization of what happens in this region when R is less than 1. We know what is happening when R is greater than square root of 2. What can we say about the efficiency hardness for this? We need to close the gap. So this is what we are trying to do right now. And also, we obtain an algorithm with complexity quadratic in time. Can this be improved? So there are some, and the most important for me is this: can we identify conditions under which the algorithm is efficient for larger R? And this is the only way to do that, is to allow physics to lead the way and to tell us what is the appropriate property that, let's say, the viscous-Berger's equation has, for which we can take advantage in order to extend this result into something that can handle a larger type of application. And this is the paper that we want. Thank you for your attention.
Konstantina, thank you so much for this thought-provoking talk. We probably have time for only one or two questions because we went slightly over time, but we can continue after that in the questions, I guess. So, any questions from the audience?
Yes.
So because you have a quantum algorithm, I assume your result is a quantum state, which means that the result of your quantum algorithm is a quantum state.
Exactly.
And therefore there should be a probability of success.
Exactly.
So what does the probability of success look like here in terms of log n, epsilon?
Okay, I don't have the actual.
And I just wonder if it's like exponential or if it's not. Or
It is not exponential, as I remember. It's often polynomial type in this case.
okay.
But let me tell you something. The way that we are obtaining this probability of success is very interesting. It is related to the way by which you prepare the state. So you have to somehow characterize the states depending on your task. You divide the states between some says good states and bad states. And you define the probability measure as the quotient, and the quotient of the L2 norm of these two quantities. And what you need is actually, you want to lower bound this probability. And it is not so much the type, if it is exponential or polynomial, it's the fact that you obtain the appropriate lower bound. You have to make this probability bounded from below by a certain quantity.
Okay. Yeah. Thanks.
Questions? So I have a quick question. Your SEI model, there are plenty of things which could be exponentially decaying there.
Mm-hmm. Oh,
So that means that, but since you were talking about the exponential decay of the norm of the
Yes.
entire solution, that doesn't happen.
no, this is exactly, it is an exponential decay of the norm.
But some of the states, some of the elements of the state vector might be more important for me than the others,
Mm-hmm.
right?
Yes.
So what happens if I am particularly interested in decaying part of the state? Let's say the number of susceptibles, which is going to zero if the epidemics got everyone either killed or infected or whatever. So if I try to use your algorithm
Mm-hmm.
in this setting, it will give me a good estimation of the components of the solution which are not decaying.
Yes. But in this case, in this particular, the norm, it is possible that the norm is not decaying in this moment. The norm of the solution, maybe element.
Element-wise?
Yes. In this particular case, you know, because we can really obtain.
So it's okay if elements of the solution are decaying exponential, provided the norm is not?
The norm is decaying.
Yeah. But that means that from the estimate of the solution, the
Yeah.
parts, the components
Yeah.
which are decaying.
They're not relative.
Yeah.
Yeah.
Great. More questions? Can continue over the refreshments. Are there refreshments? There are not refreshments. We can continue after the official end of the seminar. Let's end the seminar.
We have budget crisis too.
This is not budget crisis, this is COVID crisis. We have a Schrödinger version of refreshments. Yes.
That was very good. Okay. Oh, wow.